let us try to implement some of the methods we have seen. So I'm going to try to implement threshold-based segmentation here. In order to illustrate it, I'm going to use a random image. So this is the random image we just created. It's an image with 10 by 10 size and with values ranging from 0 to 7. I'm going to compute the histogram, and as we can see here, the histogram has, because I used the random uniform a uniform distribution in order to draw pixels, we have a fairly well distributed image in this case in terms of the pixel intensities. So I'm going to use a function that basically just thresholds using a given L value as reference. We are going to create a matrix that is all 1 values, and then we are going to set 0 pixels below the threshold. And let us try a few thresholds to obtain different results here and to see different results here. So in this case we have the original image, and this is the histogram, and when we try to use a threshold of 6, this is the result we have. We by taking the threshold as 6, most of the pixels that are considered background to be background are going to be set to 0. So in this case you can see that the resulting image have much more 0 valued pixels than 1 valued pixels. And when I use a threshold of 4, so we have accepted more pixels to be the object. So this increases the number of pixels, white pixels, in this case object pixels, and then the histogram also changes. Let us use the same function but now for a real image. I'm going to use the board image that we just have seen in the slides. This is the histogram of the image, and when we try to achieve the segmentation by using the mean intensity method, we that is 105 and something. So when we do that, we are going to take all values that are below this threshold 100 here, approximately 100, and define it to be the background. So as you can see here, it didn't consider that actually we have this peak and that the distribution here of those pixels were still falling in this case. So it would be probably much more interest to cut here around 150 or so. So defining a proper threshold can be difficult in this case, so we are going to use the Otsu method. You can later take a look at this notebook because it implements from scratch the Otsu method. What I do here is to vary the possible thresholds, and then I'm going to compute threshold and then compute first the weights and then the variances, and then find the complete equation for the variance. And we are going to use as threshold, as resulting threshold, the minimum argument of all minimum variances that were computed. So of all interclass variances that were computed in this function. I'm going to repeat the same process. You can see that it takes a little longer because I'm probing for all possible thresholds, and then that the resulting threshold is 133, which is a more adequate threshold in this scenario.